Hello students, this is second video of organometallic chemistry. So last week we have seen how the number of electrons can be counted by En rule in case of organometallic compounds. Now we shall see some of the examples. So with respect to those En rule, that is 18 electron rule. So first example here you can see is pentacarbonyl iron. So according to the En rule and some of its how to count the number of electrons in a given organic compound. So two things you have to consider here. One is the outermost shell. The outermost shell includes n minus 1d, ns, np. So this you have to keep in mind while counting the number of electrons in case of given organometallic compound. So in case of this compound iron, the outermost shell, so n becomes the outermost shell, n is here 4s, n minus 1d become n minus 1d means 4 minus 1, that is 3d. So 4s is the outermost shell and its penultimate shell, that is one shell before the 4s shell is here 3d. So we are counting number of electrons in case of metal as well as the attached ligands. So iron, the outermost shell is 4s2 3d6. So total number of electrons becomes 8 electrons. And carbonyl, each carbonyl donates a pair of electrons. So that means it becomes 5 into 2 is equal to 10 electrons. So total En for uh, pentacarbonyl iron becomes 8 plus 5 into 2 is equal to 8 electrons. Similarly, when you come to the hexacarbonyl molybdenum, so molybdenum, the outermost shell is 5s, so one shell behind is 4d, 4d5, 5s1. So metal donates 6 electrons, and from carbonyl, each carbonyl donates 2 electrons. 6 into 2 is equal to 12 electrons. 12 plus 6 gives you 18 electrons. So next example, it is a chromium. So it has 6C6H6 twice. So chromium is having 4s1, 3d5 from C6H6. So these are some of other compounds where we shall see in case of metallocenes next. So the naming is also somewhat difficult with respect to these organometallic compounds. So chromium donates 6 electrons. C6H6 donates, that is each C6H6 donates 6 electrons. There are two C6H6 molecules. 6 into 2 is equal to 12 plus 6 is equal to 18 electrons. So next, nickel cyclooctadiene twice. So nickel, the outermost electron configuration 4s2 3d8. From nickel, that is metal atom, you get 10 electrons. From cyclooctadiene, and we get 2 into 4 is equal to 8 electrons. So again 18 electrons. So next example you can see, it is an example of ferrocene. So iron is having 6 electrons. Why here iron is having 6 electrons? Mean iron is in its ionic state, that is Fe is in Fe plus 2 state. Iron individual donates 8 electrons. When it is in ionic state, that is Fe plus 2, now it becomes only 6 electrons, that is 6 electrons coming from the 3d6 orbital. 6 plus 2 into 6, that is from the C5H5. Each C5H5 donates 6 electrons. 6 into 2 is equal to 18 electrons. So right. So some more examples you can solve from your textbooks. If you have notes, you can ask. So now coming to the 16 electron rule. So the only one type of complex which obeys 16 electron rule is D8 square planar complexes. The D8, that means square planar complexes, have 16 effective electrons in their valence shell, but still these are also stable because, so we have been studying till now, when you come to the coordination compounds, if the outer, that is coordination compound having 36 electrons, they are stable. When you come to organometallic compounds, if they are having 18 electrons totally coming from the metal as well as ligand, then they are stable. But along with those rules, so the 16 electron rule is also, that is A compound, organometallic compound having 16 electron is also stable. Stability is explained here. The maximum bonding in D8 square planar complex occurs when central metal has 8 electrons. Right? So this should be keep in mind. Metal should have 8 electrons which can be accommodated in low energy dz square, dxz, dyz and dxy orbitals. The ninth electron shall have to be accommodated in the higher energy antibonding dx square y square orbital. So as is evident from the given figure, energy gap between dx square minus y square is the transition is quite large. Hence, accommodation of electrons from attacking nucleophile is the antibonding dx square y square orbital is energetically unfavorable. Consequently, d8 square planar complexes will be quite stable. In such complexes, effective number of electrons is equal to 8 coming from the central metal, 2 into 4 that is coming from the ligands. So those becomes 16 electrons. So that is extra electrons move to the antibonding orbitals. Right, so this is about 16 electron rule. So now coming to the general methods of preparation of, so I have some methods that is with respect to organolithium compounds, organoaluminum and Grignard reagents. So out of this, Grignard reagent is a very important organometallic compound. So even the person who manufactured is this compound is named after the Grignard reagent is named after a scientist Victor Grignard, and he won the Nobel Prize in 1912 for his preparation of this compound. So now we shall see organolithium compounds. So we have some methods for organolithium compounds by reaction of alkyl halide with metals. So alkyl halide here we have taken methyl iodide reacts with lithium in presence of ether at minus 10 degree to give a methyl lithium. So another method you can see is by exchange of metal and halogens. So when bromobenzene is made to react with N-butyl lithium, you get a phenyl lithium. So it is also an organolithium compound. From organomercury compounds, R2Hg, organomercury compound R2Hg reacts with lithium to give RLi. R can be any alkyl group, alkyl or phenyl group. So next coming to the preparation of organoaluminum compounds. Organometallic aluminum compound containing alkyl or aryl groups can be prepared by any of the following procedures. So when again aluminum is made to react with the organomercury compounds, you get an organoaluminum R3Al twice plus 3Hg. So aluminum chloride when made to react with RMgCl. So it gives you a mixture of organoaluminum compounds RAlCl2, R2AlCl and R3Al. Aluminum hydride is made to react with ethene, so you get an organoaluminum compound. So trialkyl aluminum compounds are generally dimeric and contain Al or Al bridges and RL bonds in their structures. Right? So this is preparation of organolithium and organoaluminum compounds. So Grignard reagent, as I said earlier, it's a very important organometallic compounds. Organomagnesium halide is generally called as Grignard reagent. So these are named after Victor Grignard, which he won Nobel Prize in 1912, who discovered them and developed their use of synthetic. So friends, we have very much synthetic application with respect to the Grignard reagent. It is used in preparation of many other compounds. Many other compounds can also be prepared by using this Grignard reagents. Who discovered them and developed their use as synthetic reagent. Grignard reagents are highly reactive and used in synthesis of alkanes, alkenes, alcohols, aldehydes, ketones, and carboxylic acids. So here, so as you see, I said, so these are used in preparation and synthesis of many other compounds. So you might have come across when you study these chapters: alkanes, alcohols, aldehydes, ketones. So most of the organic compounds can be prepared by using Grignard reagent. So it is generally RMGX is only the Grignard reagents. You come across other type of compounds like this, but RMGX, Mg is a metal. So where you come across Mg as a metal and R alkyl and X as halide, so those you can name them as organomagnesium halides. Can be called as any organomagnesium halide can be called as Grignard reagent. SOR is an alkyl RRL group. X can be chloride, bromide, or iodide. Some of the examples of this organomagnesium compounds are Grignard reagent or methyl magnesium iodide, ethyl magnesium bromide. So this can be prepared in laboratory very easily by action of alkyl halides on magnesium metal in presence of dry ether. Dry ether is pure anhydrous diethyl ether. So some preparations given: alkyl halide made to react with magnesium, presence of ether. Methyl iodide reacts with the magnesium, presence of ether. So get methyl magnesium iodide. So very simple preparations. Ethyl bromide reacts with magnesium under the presence of ether to give ethyl magnesium bromide. So these are some of the preparations with respect to Grignard reagent. So now coming to the another part, that is metallocenes or cyclopentadienyl complexes, what we call other for metallocenes. So this cyclopentadienyl group C5H5 is most important and familiar 5 electron ligand. So complexes formed by this group with transition metals are called as metallocenes. So right, complexes which are formed by using cyclopentadienyl group along with some transition metals, those are called as metallocenes. Some of the examples are given as C5H5 twice M. M is any transition metal: nickel, cobalt, iron, manganese, chromium, vanadium, titanium, etc. So out of these, ferrocene, so as we have already seen this example in EN rule, the C5H5 twice iron is the most important metallocene. We call it as, so iron is the metal. So metallocene name itself indicates. So you can replace any name of this cyclopentadienyl complex with the name of the metal. If it is nickel, nickelocene. So like that, you can give the name of the ferrocene is most important. For the first time, it was reported in 1951. So now we shall see what is its how we can prepare this metallocene that way of iron, that is ferrocene. Ferrocene is a sandwich metal complex consists of metal sandwiched between two cyclic organic ligand. Two cyclic organic ligand is 2 cyclopentadienyl group, that is 2C5H5 group. Ferrocene may be regarded as iron derivative of cyclopentadienyl anion C5H5 to the power minus, that is pi C5H5 twice iron. It's also named as bis pi cyclopentadienyl iron. So this is the other name for ferrocene, that is bis pi cyclopentadienyl iron. So you should be very much aware of this metallocene. Ferrocene, as we say, it is sandwiched between. Sandwich means middle there will be a metal, above and below there will be two cyclopentadienyl, that is C5H5 groups. So it is, we have some methods of preparation with respect to ferrocene. By direct synthesis, by the reaction of cyclopentadiene vapors with finely divided iron, so we can prepare ferrocene. Another method is by reaction of an anhydrous ferrous chloride or ferric chloride with cyclopentadienyl magnesium bromide. So you get, that is by reduction of this ferric chloride with cyclopentadienyl magnesium bromide. So you get an ferrocene. Or other way is by the reaction of anhydrous ferrous chloride and C5H6 in presence of strong base such as diethylamine. Also you can prepare ferrocene. So, right, these are some of the methods of preparation of ferrocene, a metallocene. So next we shall see so its properties, structure and bonding and remain. Thank you.